We've been getting a lot of questions on Piazza about a few specific topics. So as you're preparing for finals, I figured I would make a quick video going over a couple of those topics, explaining them in greater detail, and really just slowly stepping through the process. The first part here is going to be based on timing diagrams. This is number 5. That's one we're going to be stepping through now. It's on your mock final. If you haven't looked at the mock final, I would highly recommend you do so. There's another timing diagram question, number 4. I think they're both great questions. However, I think if you can get through number 5, you can definitely get through number 4. So I'm going to step through number 5 just for the sake of time. So the only difference here is that number 5 has 3 different kinds of flip-flops, whereas number 4 only has 2, or just 1 rather. And that's just going to make it a little simpler, a little less complications when you're thinking about behavior. However, I'm going to do my best in this video to step through things as smoothly and slowly as possible. So the first thing that you're going to want to do in situations like this, where you're presented with a timing diagram, is you want to figure out what you're looking at. You want to figure out what the expected behavior for a lot of these things is. So we've got 3 different kinds of flip-flops: a JK, a toggle, and then an SR. For the JK, the behavior is a little non-traditional in a way. So what I like to do is I like to draw out a quick behavior truth table where we have our J, our K, and then our action. Okay, so for 0, 0, we're just going to have Q. For 0, 1, we're going to have Q equals 0. For 1, 0, we're going to have Q equals 1. And then for 1, 1, we're going to have Q naught. So that Q naught is going to serve as a toggle, meaning if Q was previously a 0, it'll become a 1. If it was previously a 1, it'll become a 0, which is the same exact behavior as our T. So essentially, if there's a 1 coming in on that line, the output will switch. It will toggle. If the input is a 0, output stays the same. Now for the SR, if there's a 1 on the set, this output will become a 1. However, if there's a 1 on the reset, the output will become a 0 instead. And in this case, we'll find out that we won't have any confusion as to if they're both a 1 or anything like that. And we'll see why here in a second. So the next thing you're going to want to do, now that you've figured out what you're looking at in terms of what your flip-flops are, now we want to look at everything in terms of combinational logic. So for our JK, we obviously have our J input, and that's going to equal something, and then we have our K. For Q1, we're going to have our T, and then for Q2, we're going to have our S, we're going to have our R. Now we also, in this case, and this is another thing that differentiates 4 and 5. For 5, we have an output Z. And that's also going to equal something, and that's going to introduce a different element that, again, we don't see in number 4. All right, so for J, now we're just going to trace these inputs. For J, that's just X, nothing fancy. Now for K, if we trace this one, that's going to end up being Q2 naught. So in this case, we see the inputs of one flip-flop being dependent on the outputs of another. And that's where this can get a little hazy at times. Now for T, that's just Q0. Now our S and our R can get a little tricky, so I'm going to go ahead and trace these real fast in other colors. Apparently that's going to be tiny. Oh, and that one's huge. Got a good balance there. So for our S here, if we trace the green one, we're going to end up at Q1 naught. And then for our R, we're going to end up at Q1. Now that's where I mentioned earlier how we're not going to have any confusion with them both being 1. They're both based on the same thing. However, one is the complement of the other, which means that exactly one of them will be a 1 at all times. There's no situation where we won't have a 1 on an S or R, or we'll have a 1 on both of them. That will never happen. One will always be a 1, and the other will always be a 0. So that's going to simplify this quite a bit. Now for our Z, our output, again, we can go ahead and trace everything back. Okay, so that looks like Q1. And that's getting ORed with, let's see, oh, it's just Q2. All right, so Q1 or Q2. Okay, now for flip-flop, we're only going to update the output when the clock is at a negative edge, right? Because our instructions are telling us that these flip-flops are negative edge triggered. So it's only going to update at a negative edge. And basically what that means is, say hypothetically, I have this coming in here and I want to evaluate that, but at this edge, for whatever reason, becomes a 1. So say I'm evaluating this, say this, whatever signal this green line represents, is going to influence another signal. So at this clock cycle, I have to evaluate what's going to happen based on what's going on before the clock cycle happens. Because physically it just works out that way. And we'll see that in a more practical application once we get started here. And on that note, let's get started. So the best way to do this is just clock cycle by clock cycle, go down the list. So we'll start with Q0. Q0, again, our JK flip-flop. At this point, our J is a 0 because the J is going to be based on our X. So our X starts out at a 0. Also, before I get too ahead of myself, the instructions tell us that assume that all flip-flops are initially starting at 0. That's another thing that we didn't see in number 4, whereas number 4, you have to just assume that your input could be anything. And in that case, there's a clear which flattens it out. But you'll notice if you look at the solution sheet that there's a little box that's shaded in before that clear is activated. That's because we don't know what Q0 and Q1 were before we started looking. We can't just assume anything. But in this case, we can. So there's initially starting at a 0. So everything is starting at a 0. Now, let's think about Z also. If Q1 and Q2 are 0s, then Z is also going to be 0. So we can 0 that one out there. Alright. So, first clock cycle. Q0. J is a 0. Now, K is going to be based on Q2 naught. And if Q2 naught was a 0, then our K is going to be a 1. So we're looking at a 0, 1 here, which means that, well, Q is going to stay 0 in this case. Alright, Q1, that's our toggle. Now Q1 is based on Q0, but remember, we're evaluating that. So if this is the clock cycle we're looking at, we're looking right here for that update. Q0 at that point was a 0, meaning Q1 is not going to toggle. Now Q2 is a little more involved, has to deal with Q1. Q1 at that point in time was a 0, which means there's going to be a 1 going into this set input, which means that Q2 is going to become a 1. Okay, now we have to think about Z. For the flip-flops, we have to look at where this green arrow is. We have to look at where it was before the clock cycle. Now, for an OR gate, there is no clock. The OR gate doesn't care about the clock. The OR gate updates in real time. So essentially, Z is going to get updated immediately. So as soon as Q2 becomes a 1, so does Z. Sweet. So that's our first clock cycle down. Second clock cycle. All right. Now in this case, X has become a 1. So J has become a 1. So I'll write our J, my case. So now J is a 1. All right, well, what's K? K is based on Q2 naught. If Q2 at that point in time, right here, was a 1, then K is going to be a 0. So we find 1, 0 in the behavior table. Well, Q0 is going to become a 1 now, and that's just based on the behavior of a JK flip-flop. Let's see if I can draw a straight line. All right, Q1 based on Q0 at this point in time, we're still going to be a 0 because we haven't gotten a 1 on Q0 yet so that we can toggle. For Q2, going to be based on Q1 again, and Q1 didn't change, so neither did Q2. And with Q2 staying a 1, Z is also going to stay a 1, because again, there hasn't been anything to change it yet. So we're already in our next clock cycle. So at this point, X still a 1, so J still a 1. Now our K, at this point, Q2 naught, is a 1, meaning that's still going to be a 0. Well, our behavior didn't change, so we're still going to sit right at a 1. Now, in this case for Q1, things are going to get a little interesting, because now when we evaluate Q0, which is what our T is based on, now it's a 1, which means that we get to toggle. So at this cycle, we're toggling up to a 1. Q2, again, based on Q1, but at this point, didn't change, so neither did Q2. However, our Z could very well be different, but in this case, it's not going to be. Now at this very instant, Q1 becomes a 1, Q2 still a 1, Z still a 1. Next cycle. Now our X is back down to a 0 again, which means our K is also going to be 0. Or J is going to be 0, rather. Now our K, based on Q2 naught, Q2 still a 1, nothing new there. However, now, JK, we're just going to stay at a Q, which means our Q0 not changing. Q1, however, since Q0 is still a 1 right here, Q1 is going to toggle again, meaning we're going to pop down to a 0. Okay, Q2, well, now Q2 is going to be different, because when we evaluate it right here, Q1 is a 1, meaning there's going to be a 1 going into this reset input here. Now that means that our Q2 is going to reset and become a 0. Which also means at this instant, since Q1 is a 0 and Q2 is a 0, our Z is also going to become a 0, because we don't have that necessary 1 on either Q1 or Q2 to change or to keep the output Z high. So now we're back down to a 0. So we're getting some interesting behavior. Things are changing around a bit. All right, so for the next clock cycle, our X is back at a 1 again, which means that J is a 1. But now, K, being based on Q2 naught, Q2 was a 0 here, which means K is also going to become a 1, which means we're going to toggle the output Q, which means Q naught, or Q0, is going to become a 0. So for Q1 then, we're still evaluating it right before that clock cycle. Q1 is going to toggle another time, putting it at a 1. Q2, again being based on Q1 at this instant here, where it's a 0. Now we're going to go back to set again. So Q2 is going to return to 1, or high output value. Z, if we evaluate Z, which is Q1 or Q2, in both cases Q1 and Q2 are 1, so Z is high again. Next clock cycle, our X is 0, which means our J is 0. Now K, being based on Q2 not, Q2 at this point was a 1, which means K is going to be a 0. With a J 0, K 0, we're just going to stay constant with our Q, which means Q0 is going to stay at 0. Okay, Q1 being based on T, which is based on Q0. Now Q0 at this point is a 0, which means we're not going to toggle at this point, which means Q1 is going to stay at a 1. Okay, so now Q2, again being based on Q1, Q1 right before the clock cycle was a 1, which means there's going to be a 1 going into the reset, which means Q2 is going to become a 0. Now Z, being based on Q1 or Q2, Q1 is a 1, Q2 is a 0 now, but that's enough to keep Z high. Alright, only a couple more cycles to go here. So at this point, X is a 1 again, which means our J is going to be a 1. Now our K, being based on Q2 not, Q2 not was a 0, which means our K is also going to be a 1 again, which means that our Q0 is going to toggle. And if Q0 was previously a 0, that means Q0 will now be a 1. Okay, now our toggle flip-flop being based on Q0. If Q0 was a 0 right before the clock cycle, that means that Q1 is not going to toggle and it's going to stay the same. Q2 being based on Q1. If Q1 right before the clock cycle was a 1, that means we're still going to stay at a 0 because we have a 1 going into the reset. Now at this point in time, Q2 is a 0, but Q1 is a 1, which is enough to, again, keep Z at a 1 as well. Last clock cycle here, our X is at a 0, which means our J is a 0. Now K, being based on Q2 not, Q2 at this point was a 0, which means Q2 not is going to be a 1. It's going to give us a 0, 1, which means that our Q, in this case, will become a 0. So that's just a 0. Now, we don't know what happens after this clock cycle, and honestly, we don't care. So this just goes off into the void as a 0. Alright, Q1, our toggle flip-flop being based on Q0, right before the clock cycle is a 1, which means we're going to toggle. And if we were previously at a 1, we're now going to be at a 0. Now, Q2 being based on Q1, Q1 before the clock cycle was a 0, which means that we're going to, was a 1 rather, sorry, getting tripped up here. That's why it's important to really take your time here, pay attention to what you're doing, write things out if you have to, but don't rush it. Trying to rush through these doesn't make them easier, then it doesn't improve accuracy. So take your time, be careful, just one step at a time. So back to Q2. Q2 is being based on Q1. If Q1 before the clock cycle was a 1, that means we're going to have a 1 going into the reset, which means Q2 is going to stay low. Off into the void it goes. Now at this point, with Q1 being a 0 and Q2 being a 0 as well, Z, which is Q1 or Q2, doesn't have that necessary 1. So now Z is going to go back down to a 0 and stay that way for as long as we can tell. So that is a general approach at how to do the timing diagram questions. My general recommendation here is just to take your time, be careful with it, don't try to rush it, and just go clock cycle by clock cycle. If you try to work ahead in any way, it's not going to make anything easier, and odds are it'll just add confusion to the problem. So take everything step by step. It can be overwhelming at first, but practicing these is key. Practice, practice, practice. If you Google timing diagram questions, you will find good resources out there. There are questions in the modules. Again, there's number 4, which is another timing diagram question. But practice makes perfect here. Alrighty, so for the next part, we're going to be looking through number 1, which is essentially we're given one truth table, and then we're asked to find a bunch of different ways to do essentially the same thing, build the same circuit. And we're going to go in a little bit of a different order than the mock final, and we're going to go ahead and we're going to start out with the programmable logic devices. Starting off with the PROM. Now the PROM, as you can see, these X's indicate that these points are fixed, meaning you can't change them at all. The way they are is just the way they are, and there's nothing you can do about it. However, you will notice that over here there's nothing going on. This is where the programmable aspect of the PROM comes in handy. Now, you'll notice that these X's represent a little bit of a pattern, and that's actually highly indicative of the way we set up the truth table. So these would all be zeros, so 0, 0, 0, 0, 1, 1, 1, 1. Whereas if we come over to the truth table for A, 0, 0, 0, 0, 1, 1, 1, 1. So these basically just represent the truth table in row order, actually. So if we number out the rows here, 4, 5, 6, 7, and then we number them out here. That'll make this a lot easier. Now when we're going to represent things that we're programming, I can do it with a circle. So if we see that we're going to have a 1 on row 1, I'm going to find row 1 here, go over here, and then there's going to be a circle right there. Now that's me saying that, hey, I'm programming this PROM, and this is a PROM, to activate on row 1, right? Because in actuality, these are all going through somewhat of an OR gate, and it's just choosing one of many there. So I'm just going to keep doing that same thing. So it might be easier to consult the shorthand method of writing these out, where we're going to have, and this is another question, I believe, where we'll have row 1, 3, 4, 5, 6, and 7. Alright, so that helps a little bit. So now I can go 1, so 3, 4, 5, 6, and 7. So not too complicated there. It's really just understanding what the PROM is and kind of what it is you're looking at, what it is you can program. So then we're moving on to the next section, which is going to be involving a PAL chip or a PAL type array. And the way this is going to work is these are fixed now. Previously, this was fixed, so we'd have x's here. So now, in a way, we have our x's on the other side, where we can program. So in a way, it would be like for the PROM, the x's would be here, and now we can draw circles over here. That's kind of the way it's looking. However, for this, we can't just go based on row number. We have to do a little more work than that. We're going to have to figure out basically a logic expression that we can use to essentially find it out. And the best way to do that is to go ahead and make a truth table. So what I'll do, so I'll go ahead and I'll write out the truth table here. And again, this is all part of the mock final, which again, if you haven't done it, I would highly recommend you do so. 1 0 0 0 1 1 1 1 0. All right, and then we can go ahead and fill in. All right. So now if we go ahead and we complete our groupings, we can group 4 right there, and then another 4 right there. So essentially, we find that F is equal to A and C. Okay. So this is pretty simple. It doesn't make for too interesting of a PL or PAL here, but I'll go ahead and simulate what some other functions might look like as well. So in this case, we just need two of these lines here. The first one is just A. So in that case, I'm just going to circle an A. And the next one is just C. And that's on a different input line there. So, and that's it. That's really it. There's not a whole lot going on there. You just need the minimum sum of products expression, which we found to be A plus C. Now, let's say for the sake of the example that we had plus A naught B C naught plus A B naught C naught, right? So we're adding on two expressions there. How would we represent these as well? Well, we're just going to go find them. So A naught, so in this case, this first row here, that was A. And then this was C. So in this case, this is going to be A naught, B, C naught. That one's going to be A, B naught, C naught. Right? And these are purely hypothetical. I did not get these out of the truth table or any of the question. They came straight from the top of my head, just for the sake of showing you what the example would look like. So in this case, we need A naught. So I'm going to find A and then A naught. B, C naught. And that's it. Same thing for the fourth one there. A, B naught, C naught. And that's it. Really not too complicated in the setup. It's just, again, knowing which parts you can program and which parts you can't. So the mock final actually didn't include it, but there is another kind of programmable chip that we learned about. This is the PAL, and that is the PLA. Now the PLA is cool because you get to program the whole thing. It's not just where you get one side and the other side's fixed. In this case, we'd actually where we're going to have another programmable line that's going to be connected to another OR gate. See if I can draw an AND gate, or an OR gate, rather. Okay. And then that's going to be our F. Okay. So again, for the sake of the example, I'm going to keep reusing this more complicated statement for F. So, again, it's literally going to look like the same thing here, where we'll have A on one, C on another, and then A naught, B, C naught, A, B naught, C naught, right? So that's it for the left side, and then for the right side, it's kind of boring because there's only one output, but we're just going to circle all of those. Now again, for the sake of argument, say we have a G. We have our output G, and that's going to be A, B naught, C naught, plus AC plus A naught B. Okay, so now we have another output, but the PLA makes it easy because realistically we could just add on more. I'll use the ruler here. Alright, so I've skipped ahead in the video just a little bit to draw out the rest of the PLA. Now again, remember, this is entirely hypothetical. It's not in the question anywhere, and it's not something that there's any actuality behind it. It's all off the top of my head here. So the PLA is super useful for having more than one output. In this case, we'll have two. So essentially what we can do is we can just look at G individually as well. But we'll notice that this first term, A, B naught, C naught, is actually a part of F as well. So instead of programming it on another line, all I have to do is find the part of F where I programmed this, which is going to be this line right here. And I'm going to program that into G as well. And all I have to do that is draw another circle. And I can do that because that's just the way the PLA works. I can save myself a line there. So in theory, if I needed more than the allotted 8 options here, I could do that as long as I can double some of them up. And again, it's the same process. So we'll have A, C, and then A naught, B. And again, those are going to G. And that's the PLA. The PLA is by far the most customizable option, but again, there is more to it than the others. Now, all three of these are going to do the same exact thing with the exception of the PLA having the G output as well. So it's just more ways of doing the same thing. Now, we can extend this even farther by considering multiplexers and decoders, which is what we're going to go ahead and look at next. So the multiplexer and decoder are ways of choosing an output based on some sort of selection process. So the first one we'll go ahead and look at is the multiplexer. And this is part F of the question, for those of you keeping score at home. So part F features an 8-to-1 multiplexer. And we get 8-to-1 because we have 8 lines here. 7, 8. And that is 0. And that is 8. And since we have 7, sorry. And since we have 8 different inputs there, all funneling out to one output, we're going to need 3 select lines. S2, S1, and S0. Now again, this is pretty simplistic because everything is lining up. So if I go ahead and drag our truth table down here, so I can see what I'm working with, there's not a whole lot of work here. Essentially, again, we're just taking these direct outputs here for F, and that's it. That's all we have to do. So 0, 1, 0, 1, 1, 1, 1, 1. That is all. That's all we have to do. However, we do need to make sure that we program in our select lines as well. A, B, and C. Now it's important to note that A, being the most significant bit, is going on S2, which is the most significant select line. It's important to make sure that those are lined up in that fashion so that you're getting all that you need to. Now, for the sake of playing the hypothetical game some more, let's say we don't have an 8-to-1 mux. It doesn't exist. We only have 4-to-1 mux. How can we make that work with this same logic? I'm going to drag that down again. So for 4-to-1 mux, have the multiplexer, 4 input lines, and we'll go 0, 3. And since there's 4 of them, that means we're going to have 2 select lines. And our Y, which is just going to end up being our F. So how do we do this? Well, the easiest way is to break up the truth table based on your 2 most significant bits. So we have 2 select lines. So I'm going to dedicate the most significant select line, S1, to A, and the least significant, S0, to B. Now what that allows us to do is we can group the truth table based on where those 2 select lines produce similar patterns. So you notice in all 4 boxes I've chosen S1 and S0, or A and B, are the same the entire time. So with this in mind, we can group the truth table into 4 parts, which is great because we have four options here. Now we can look at each part individually, so this being one part, that being another part, and we can determine, well, what would our input have to be in order for us to, get the desired output. So for this one, if we look at C and we look at F, they're exactly the same, right? So all we need for the input there is C. And that's the same thing for this second part. So first, second, third. Actually, maybe more accurate here. 0, 1, 2, 3. So that's C. That's C as well. Well, that's always 1, and so is that. So again, there's our answer. C, C, 1, 1. And again, we have A and B as our select lines. Now again, let's play some more hypothetical game. What if these 2 were zeros, and this one here was actually 1, 0? Then what? Well, it's the same logic. So this stays, 0 stays C, and 2 stays 1. But now I have to consider 1 and 3 again. Now, 1 is just the direct opposite of what C is. So we can simply just do C naught. And for 3, again, it's constantly a 0. So we can just put a constant. So again, on 1, we'll have C naught. And on 3, we'll have 0. So that is a situation where you're given a multiplexer that doesn't really fit the situation, but in a way it still does. So the last thing I'd like to go over is the idea of a decoder. So in the case of the multiplexer, we're taking many inputs and we're turning out one output. The decoder is a little different in the sense where we're taking 3 inputs and then deriving many outputs, which we'll see here in a second. And again, this is part H on the mock final, for those of you keeping score at home. So we'll start out with the 3 to 8 first, and then, as I'm sure you'll expect, we'll go ahead and mix it up for our later questions. So again, I want to choose my most significant select line, S2, as my most significant bit, or A, like that. And I always want this to be enabled because there's no reason for it not to be. So again, all we're going to look at is these row numbers where we have a 1. So that's 1, 3, 4, 5, 6, 7. And all I'm going to do here is I'm going to extend these 1, 3, 4, 5, 6, 7. From here, let me move this off to the side. All I have to do is get one big OR gate. I can find my output F. And that's all. So my 3 inputs here, we'll choose one of these, and then for the one chosen, we'll put an output of a 1 out, and then that's the logic. That's all. Nothing too complicated. Everything works. This is the proper size decoder for this set of inputs in this situation. But, you know, true to form, what if we don't have a 3 to 8? What if we've only got a 2 to 4? Well, what are we supposed to do then? Well, if we have 1 2 to 4, we're kind of out of luck. There's not a whole lot we can do there. But if we have 2 2 to 4 decoders, now we're talking. So again, just like we did with the mux, we need to find a way to split up the truth table into parts that make sense for us. Disregard this, that's from another section. So how can we split this up? Well, if we split the truth table in half, well, now we've got something we can work with. Now we have, if we were to take A out of the equation, now we can have 2 separate 2 to 4 multiplexers, where you'll notice A or B and C are the same for both of these sections here. So let's think about it that way. Okay, so we're going to need 2 2 to 4 decoders. So we'll dedicate this top half of the truth table to this guy, and then the bottom half to the one on the bottom. Okay, so we'll have B and C for both. And then let's think. So if this is 0, 1, 2, 3, then this also has to be 0, 1, 2, 3. Now in this case, we're going to need all 4 of those. It's going to go into a big OR gate, which I seem to be unable to construct. Those all go into an OR gate, and then we'll go ahead and do the top half. Well, we'll need line 1 and line 3. Again, into one big OR gate. And that's it, right? Well, not quite. As you might expect, we'll need to take these 2 separate OR gates. If I can select all of the truth table, we'll need to take these 2 separate OR gates and then turn them into one final OR gate that will give us F. But you'll notice we never used A, or at least not yet. A was how we were able to split it up, because for this bottom half, the entire time, A was a 1, and then for the top half, the entire time, A was a 0. So hey, maybe, if we use the enable, maybe we can make this split work. So if I want this top half to be enabled when A is a 0, well then I can just put A naught. as the enable. That way, when A's is 0, this top decoder will get enabled, produce its output, and then that'll become F. But likewise, we'll need to put A as the enable on the bottom. That way, only one decoder is activated at a time, and then with B and C, the correct output will be achieved. So, again, you can make incorrectly sized hardware function the way you want it to just by breaking up the truth table. In both cases, with the multiplexer and the decoder, it's just a matter of how you want to break it up. But again, if you break things up based on, in this case with the decoder, based on the most significant bit, you can get clean groupings, and then everything will work out. So that's it. If you have any questions, please post them on Piazza. Again, the final exam is now posted. Again, if you have any questions, if you notice anything wrong about this video, please let us know. Otherwise, good luck with your final and everything else that you're working on. And I hope this video helped.